Welcome students to video class number 30, and we are continuing our discussion on the stability analysis using Bode Plot. That's part 3. Now in this session we are going to start with an example. Now only you will be understanding the concepts that we have already discussed regarding Bode Plot. Now let's start with a simple question. The question is, construct the Bode plot for the system whose open loop transfer function is given by GSHS 4 divided by S into 1 plus 0.5 S into 1 plus 0.08 S. Okay. Now the same question I have rewritten in another form, that is 100 divided by S into S plus 2 into S plus 12.5. This is usually an open loop transfer function is given by keeping this S isolated every time. So far in the previous method, when we did the root locus or when we did RH criterion and all those things, we are comfortable with this and we will straight away do this. But this question is exactly this question, and you may be wondering, what is this 100? Here you have 4 and here you have 100. We'll see that. See, we want to make this in this form, right? 1 plus, that is the term that comes along with the S, the term that is to be added along with this S, that is to be isolated. Now here, in this case, this 2 and 12.5 has to be taken out, then only this will become 1 plus S form. This has to be converted into 1 plus S form, or that forms the skeleton of Bode form. Okay, hope you are remembering in the part 1 video. Look at this. We have actually started with this S plus T1 exactly like this, right? S plus T1, and what we did was we took T1, T2, all those constants outside from those first order terms. These are called as the first order terms. S1 plus, these are all first order terms. So from this first order terms, what we did is we took the constant out so that this becomes 1 plus S form, right? And when you put S is equal to J omega, that becomes a sinusoidal open loop transfer function. And not only that, since this is of the form 1 plus some S, this is actually called as a Bode form of the open loop transfer function, sinusoidal open loop transfer function. So in order to have that what you need to do is you can straight away take this 2 and 12.5 outside, right? So that you will get this as S into 1 plus S by 2, 1 plus S by 2, which is 0.5 S. Okay, and when you take 12.5 out, you will get 1 plus what? 1 plus 1 by 12.5, which is actually 0.08 S. Okay, you can just do it by yourself, and you have taken 12.5 into 2. That means this is 25, right? 12.5 into 2 gives you 25, or when you do the cancellation, you will get this as 4 divided by S into 1 plus 0.5 S into 1 plus 0.08 S, which is exactly the same question. Okay, now let's start to do the procedure of constructing the Bode plot. So I'm going to explain it in step by step, and you should also follow that. So step 1 is to obtain the sinusoidal transfer function in Bode form. That is very important. Not in this form. Okay, by making all the constants that comes along with the first order factors to be 1. So you need to take all those constants out as I have shown in this example. Okay, so that here in this question it's already given in the Bode form, right? This is of the form 1 plus 1 plus. So you don't have to do this. Now the question would have been like this. You should do this stuff and bring in this form. And this is not enough for finding out the Bode form. You need the sinusoidal transfer Now, how to do that? Now, to obtain the sinusoidal transfer function, put s is equal to j omega in the Bode form, so that you will get the transfer function as g of j omega into h of j omega is equal to 4 divided by j omega into 1 plus zero point 0.5 j omega into 1 plus zero point zero 0.08 j omega. Okay, right? So that's your step one. Now, as I've already explained yesterday, that Bode plot consists of two plots, that is the magnitude plot and the phase plot. Okay, so first of all, our intention is to find out the magnitude plot, and there comes the, so in order to plot the magnitude plot, there comes the step 2, which is actually the initial slope of the Bode plot. Okay, initial slope of the Bode plot. Now I'll be explaining a general case, and then we'll apply that to this problem. Okay, so how to find out the initial slope of the Bode plot, then only we can use all the rest of the terms as I discussed in the live class yesterday. Okay, now let's see a general case of how to find out the initial slope. Say consider a constant by j omega raised to n. Now how to find out the magnitude? I mean, by the slope of this initial slope, this step is exclusively for finding out the magnitude plot. So now when you take this magnitude in decibel, this will be 20 log k minus 20 log the magnitude, right? Magnitude of j omega is log omega root of omega square. The whole raised to, this is whole raised to n, right? You can bring this n to this side, so that this becomes equal to 20 log k minus 20 n times log omega, right? Now let us start with the basic some examples. So suppose your n is equal to 0. N is equal to 0 means the magnitude of this factor. Okay, so when n is 0, this term becomes equal to 1. So the initial Bode plot, or the Bode plot, starts from 20 log k, right? 20 log k. You don't have to consider this because n is 0. So that means this is equal to 1. 20 log 1 is 0. So it is 20 log k. That is the initial slope of the Bode plot for a case of a type 0 system. Okay. Now let us consider the case where n is equal to 1. That is, this is a type 1 system. Now type 1 system will be having different initial slope than a 0 type system. Okay, let us see that. So your term becomes k by j omega raised to n, where n is equal to 1. Now how to find out the magnitude in decibel? This is equal to 20 log k minus 20 log omega, right? 20 log omega. Now this is actually the magnitude plot. So this is having a fixed value if k is known. So in this problem, k is equal to 4. So k is equal to 4, right? Now this is the point that you should be very careful about. Or possible to commit a mistake by taking 100 as a constant. No, it is not. Because I mean, the constant has to be the constant when this becomes in the Bode form. The first thing is you need to convert it into Bode form. On conversion, you will be having some amount of cancellation, and after cancellation you will be obtaining a constant that has to be considered as k. Don't take this 100 as k. Actually, in the real problem, k is actually equal to 4. So 20 log 4 is going to be a particular a fixed value. Now from that point onwards, there is always a decline of, the meaning as is actually, this is like this is plus of a line. This represents, what does this represent? This is actually a, yesterday as we studied, this is actually a 20 decibel per decade, right? So this is actually a fall of 20 dB per decade. That means if you try to draw this is having a 20 log k, right? 20 log k. From this point onwards, this is going to decrease at a rate of minus 20 dB per decade. Now the question is, so suppose from where it will start, that's an important point, say from 20 log k, will it be, now we must be very careful about how this is actually the 0 dB axis, right? Now if we can understand when will this become 0, that means this particular line has to meet the 0 dB at a particular omega. So if you can find out that, it's very easy to construct this initial slope. Now what will be the, so that means, so at a time, so it starts from 20 log k, and from there onwards it decreases as per this rate, minus 20 dB per decade, because it is just the sum. It is similar, it is like this. If you can individually draw this is actually the constant, and we do not know where it touches this particular thing. So this is having a, so when you combine this there is always a reduction, right? This much will be reduced at every time, so that it follows this, right from the beginning. That's why I told you this k by j omega raised to n determines the initial slope of the Bode plot. Now the question is, at which point of frequency, this actually varies according to the frequency, because this is omega. As omega varies, this is a fall. So at a particular frequency, this will be meeting 0 dB. So that you can find out by equating this thing to 0. That's what we want to, this actually represents what? This actually represents 20 log k minus 20 log omega. So that means if you can equate this to 0, you will be able to find out the omega at which this particular line meets the 0 dB. So this is 20 log k plus minus 20 log omega is equal to 0, or 20 log k is equal to 20 log omega, right? Isn't it? So what will be this? So when you take the anti-logarithm of this you will be getting this as k, this and this get cancelled. Taking the anti-logarithm, you will be getting k is equal to omega, or the frequency, this is actually the frequency at which k by j omega touches what? Touches the 0 dB line. Okay. Now if you know this point, from this point you can find out what? You can draw a line which passes through this point at a rate of minus 20 dB per decade. Now I will show you how to draw that. So okay, now in this question it is of the form 4 by j omega, so this comes under this category. Now let me show you one more thing. Say consider n is equal to 2. Okay, so then only you will understand the difference. So this is a type 2 system, right? This is a type 2 system. In this type 2 system, the equation becomes k by j omega the whole square, and if you express the magnitude in decibel, you will get this as 20 log k, okay, minus what? 20 log omega square, right? This is 20 log omega square, or you can come to another this thing. So this is 20 log minus 40 log omega. Now what is the difference? In the type 1 system, this reduces at a rate of minus 20 dB per decade, while in a type 2 system, it starts from the 20 log k, but it reduces at a different rate, that is at minus, so this will be 40 dB per decade. So for that, what we need to do is we need to understand this frequency at which it touches the 0 dB. That's why we are finding out that. Now here also, this particular line meets at a particular frequency, it will meet the 0 dB. So how to find out that? Equate this thing to 0. Equate this thing to 0. So when you equate this 20 log k is equal to, say this will be 40 log omega. When this is equated to 0, this becomes 40 log, right? Okay, so you'll be getting this as 20, this is 2, or you can take, so this is 20 log omega square, or taking the anti-log, you will be getting omega is equal to root of k. Now what is this? So this is actually the frequency at which k by j omega square touches the 0 dB line. So this is the frequency. So when you find now this, that is, it is root k. Now can you just guess what will be for n is equal to 3? N is equal to 3, the frequency will be the cube root of k, that is k raised to 1 by 3, right? So for n is equal to 4, you can find out your omega to be k raised to 1 by 4. And for n, it will be omega is equal to k raised to 1 by n. Okay, so this is very important. So this is actually the frequency at which that particular term touches the 0 dB. Once if you know that frequency, from that frequency it's very easy to draw a line with that particular slope. Okay, with that particular slope, we know that. So in these two cases, we know that see, through this point, this line passes at a rate of minus 20 dB per. So if you know this point, from this you can very well draw the, so you don't need, I mean, you won't be having a confusion regarding the starting point. So it will be arriving at this point. So you will understand it when we do this problem. Okay, fine. So this is a second step to find out the initial slope of the Bode plot. And in this question, the initial slope is determined by 4 by j omega. So the number one thing is you need to count this, it is a type 1 system. And we have already seen that in a type 1 system, the frequency at which this k by j omega meets is at a k is equal to omega, right? K is equal to omega. So you can see that or omega is equal to k, that is at that frequency this touches the 0 dB line. So from this you can understand that omega to be equal to k, which is actually equal to 4 radians per second. So it is at this this frequency, this the Bode plot represented by this transfer function passes. But that's not the exact Bode plot. We are just worried about the initial slope. Once if you know the initial slope, then finding out the corner frequencies, you can simply draw the slope of other terms. This is the greatest issue or the primary issue of drawing a Bode plot. So first of all, the initial slope is determined by 4 by j omega. So from this you understand it is a type 1 system. If it is a type 1 system, then the frequency at which this particular thing crosses the 0 dB at 4 radians per second. Now let me show you how to draw the initial plot from in a semi-log graph sheet. Okay, so here is about a semi-log graph sheet. So when you look at the semi-log graph sheet, when you look at the horizontal, so you have, as a normal graph, you have one vertical axis, okay, and when you look at the vertical axis, it is numbered, the divisions are numbered as 1, 2, 3, 4, but there is a difference. The divisions are not evenly distributed. The divisions are uneven, or the divisions are not equidistant to each other. Okay, so look at this. So there is a gap of 1 to 2, there is a big gap. From 2 to 3, the gap reduces and it goes on in such. So it's not a linear between the divisions there is no linear variation. So that means this is actually this axis is, or the horizontal axis is logarithmic in nature. Okay, now why do we need this logarithmic? That is to include all the frequency. That means the first point that you need to understand is I will have to draw this horizontal axis has to be taken as the frequency axis. Say you can call this as log omega. Okay, and now the thing is that this is expressed in radians per second. This is expressed in radians per second. Okay, so this is the first thing that you need to understand. This axis, okay, so we'll be drawing that. Anyway, this axis is log of omega. Now coming to this vertical axis, you can see that say, look at this. This is a bold line in comparison to the rest of the lines, but the next bold line is this. So you can see that there are 10 equally spaced divisions. Now from this to this you have 10 equally spaced division. From this to this is 10 equally spaced division. So this axis is exactly the same as the normal graph sheet. So what you find out is the vertical axis is just like a normal graph, while the horizontal is logarithmic in nature. That's why the name semi-log. Okay, now we have already assigned this axis for what? Axis for the frequency, because that frequency is expressed as logarithmic scale, and I have already explained why do you need to take this logarithmic scale. That is to accommodate all the frequencies. Now in this, what will be a plot? So this axis you will be plotting the magnitude in decibel, right? Magnitude in decibel. So okay, now in step 3 what you need to find out is the corner frequencies of the, in this problem it is the of the first order terms. So what are the first order terms? Any terms of the form 1 plus some s. Okay, so you have two terms in this problem, that is 1 plus 0.5 omega j into 1 plus j into 0.5 omega and 1 plus j into 0.08 omega. So yesterday we found out how to find out this corner frequency. Say, let us call the corner frequency as omega corner, and this omega corner is given by what we found out is take the reciprocal of the term that comes along with j omega, the quantity that comes along with the, okay, so it is 0.5, it is equal to 1 by 0.5, which is equal to 2 radians per second, right? Now what about the corner frequency of this? The corner frequency of this term is what? This is actually 1 by 0.08, 1 by 0.08, or that is equal to 12.5 radians per second. Okay, right? Now you can have a tabulation if you want in the increasing order of the corner frequencies. So you can write like this. You can create a table terms, then the magnitude okay, or the slope of the magnitude of the individual, the slope of the magnitude, and this is the corner frequency. Okay, so you can tabulate this. So number 1, the term is, so you must arrange this in the order of increasing order of the corner frequency. So the first corner frequency is 2 radians per second, that is of the term 1 plus j 0.5 omega. Now what will be the slope magnitude of this? This will be offering, this is actually it is actually 1 by, sorry, these are the two terms, sorry, 1 by, don't forget that. So the first term will be 1 by 1 plus j 0.5 omega. So we have seen yesterday itself that it offers always a slope of 20 dB per decade, and the corner frequency of this term is 2 radians per second. And what about the second term? Second term is 1 by 1 plus j 0.08, and this again offers another minus 20 dB per decade, and the corner frequency is 12.5 radians per second. Okay, this is radians per second, this is also radians per second. Now again I'm going to have a recap of those things which we studied. That is, the importance of corner frequency is, up to this frequency, up to this 2 radians per second, this has no effect, right? Because this offers a 0 dB. The effect of this term occurs only after 2 radians per second. That means, coming to this this log, this is your 2 radians per second, right? Now, till this 2 radians per second, the term 1 by 1 plus j 0.5 omega has no effect. Now, what about this term? This term, anyway, the corner frequency is much higher than this. That means till 12.5. So, from this figure, where is the 12.5 point? This is your 2. If this is your 2, this must be 20, right? So, 12.5 has to come between, this is 10 and 12.5, right? So the 12.5 has to come out somewhere over here. So at this frequency only, this particular term will be having an effect. That means till that point, that will be 0. So we have all the data. We have obtained the data required for plotting the magnitude plot from the given g of s, h of s. So let me just have so we got the initial slope of Bode plot, which meets at the 0 dB axis at 4 radians per second. So this is an important parameter required. And the other two are the corner frequencies of each term, that is 2 radians per second and 12.5 radians per second. So I'm going to rewrite those things. Okay, here is it. So I have had the initial slope which meets at 0 dB. Since it is a type 1 system, we have seen that initial slope will be always for a type 1 system, the initial slope will be minus 20 dB per decade. So it starts itself with the minus 20 dB per decade, and then so anyway this meets 0 dB. Before it meets 0 dB, there is a first corner frequency, that is 2 radians per second, due to one of the first order term, that is 1 by 1 plus j 0.5 omega. So that means after this, the impact of this is adding another minus 20 dB per decade to the already declining slope. So that means minus 20, again minus 20, that results in minus 40 dB per decade. That is the effective fall. Then this plot moves at a rate of minus 40 dB per decade from 2 radians per second. And finally, the second corner frequency comes at around 12.5 radians per second. And this also offers another minus 20. So effectively, it will be offering a minus 60 dB per decade. So the effective Bode plot, the importance of corner frequency is the Bode plot for this question actually falls at minus 40 dB per decade from 2 radians per second onwards, and from 12.5 radians per second onwards it is going to fall at a rate of minus 60 dB per decade. So you'll be understanding when we start to plot the Bode plot. Okay, now these are the essential parameters that are required for plotting the magnitude plot. So do you remember, here we are only in the first part of the Bode plot, that is the magnitude plot. Okay, so here is the semi-log graph paper. So along this, I'm marking this axis as a 0 dB axis. Okay, now so along the vertical line you can mark the magnitude. So this side I am using for magnitude, as I have already explained, magnitude in decibel, while This is actually the logarithmic frequency. This is for the logarithmic frequency or logarithmic omega. Now you don't have to convert this omega into this 4 and 2 and 12.5 into log, because when you plot these figures here, it will be automatically plotted as logarithmic of this value. What you just need to do is just identify these points on this and plot accordingly. So you don't have to you don't need any conversions. So anyway, this is your 0 dB. Now if this is your 0 dB, now we have seen in the requirement we need to represent minus 20 dB, minus 40 dB and minus 60 dB. So here all we can see a negative slope. That means we will be more needed along with the negative slope. So that's why I have placed the 0 dB not exactly at the center, just above, because more than the positive value we require the negative value. So you can just make it a slightly higher than the center point. It's customary always to select the almost the center point of the graph as the reference point. Now here in this magnitude plot, 0 dB is selected accordingly. Now if there would have been some 20 dB plus 20 dB over here, say one is plus 20 and something like that, then you can move this reference down. Okay, so based on these values you can select the 0 dB. That all you will understand when you do problems. Okay, now this is 0 dB. If this is 0 dB, you can mark this as 20 dB plus 20 dB. So that means one full division is equal to 20 dB along the y-axis, and this can be called as then the 40 dB. So this is magnitude in decibels. So obviously this will be minus 20 dB, right? This will be minus 40 dB. This will be minus 60 dB, and it goes on like that. Okay. Now what you need to do is how to start with. So we will be doing first of all with the initial slope of this Bode plot. The initial slope of the magnitude plot actually touches the 0 dB at 4 radians per second. Now let me show you which is this 4 radians. So in order to obtain this 4 radians per second, now look at this frequencies. Now you have a frequencies starting from you have 2 radians as the first corner frequency, another frequency which is the initial slope meeting at the 0 dB, that's at 4 radians per second, and you have 12.5. So that means that these are the values in between 2 decades, right? So these are the value that comes in between this is 4 and 2, right? So it will be a value that comes in between 1 and 10, right? 1 and 10 decades. So that means you can select this as this point as 1. This as along the x-axis you can mark this as 1, this one as 10, this one as 100, and so on. So that means when you plot, when you, I mean, these two points 4 and 2 comes within this decade, that is within this decade. Now what about 12.5? 12.5 is something which comes between 10 and 100, and I have already told you yesterday that this line represents, since it is 1, it starts from 1 radians per second, this must represent 2, this is 3 radians per second, 4 radians per second, and so on. Now when it comes to this becomes, the decade has now changed to 10. Now you have only the multiples of 10. That means this must be 20, this must be 30, this must be 40. So your 12.5, that is one of the corner frequencies, the 12.5 has to come in between these. Am I right? Since this is 10 and this is 20, 12.5 has to come between this, and we will find out that. Okay, anyway, now let us move on to the first thing. That is, the first step is to, while drawing the magnitude plot, first step is to draw the initial slope of the Bode plot. So the initial slope actually depends on the value of, as I have shown here, it depends only on the value of 4 by j omega, and you must also understand that is not the Bode plot, that is just a part of a Bode plot, and the Bode plot will change as the corner frequency comes into play. Now let's see how to find out this 4 radians. Now what must be this 4 radians per second? Now this 4 radians per second is actually the point corresponding to this, right? So you can have this, so this is your 4 radians per second. Okay, this is your 4 radians per second. So you may just mark that 4 radians per second over here. Okay, so this is your 4 radians per second, right? Now in this 4 radians per second, what I want to now you must draw a line which passes with the slope of minus 20 dB per decade, which passes through this line. That's what it shows, right? The initial slope, that is when you try to draw this 20 by k by, that is, if you are to plot the graph of this, what you're going to get is this will be 20 log 4. Now this is basically 20 log 4 minus 20 log omega. So that means that will be like this. So this slope meets at, what it says is it meets as 4 radians per second. So you must know how to draw a slope passing through this. Now if this is considered as the initial point, that is a 4 radians per second, what is the next decade after this point? So the next decade, if this is 4, you need to mark 40 in this. So the 40 comes over here, right? So this is 40. Why? Because this is a section corresponding to the decade, right? So this is the point corresponding to 40 decades. One decade. That means this is 4 radians per second. So 40 radians, as it moves to 40 radians per second, we say a decade, it has traversed a decade. So this is a decade length. Now from this point, now if you can, now what is this point? What is this point? This is actually your minus 20 dB line, right? So this is actually your minus 20 dB line, right? So mark that on the 20 dB line. Here also you may mark that on the 20 dB line, right? So what does this suggest? As a, see, this is actually, now from this 4 radians per second, if the graph continues in that way, it is always offering a line must pass through this, which is having a slope of minus 20 dB per decade. As it moves from 4 to 40, this magnitude has to reach at this point. That means it is 20 dB per decade. So if you can plot a line like this, which passes through this, what is the slope of this line? Yeah, this is a line which passes through this origin. So that means this slope is actually 20 dB per decade. So this is the initial value. Now the question is, will this initial slope, so to the actual question, that is in the actual magnitude plot, will this is having a slope of 20 dB, minus 20 dB even at 4 radians? The answer is no, because you have the first corner frequency comes into play at 2 radians per second, which is less than 4 radians. So what is that 2 radians per second? So 2 radians per second is a point coming over here, right? So you can just mark it on that, and till this point you can just have a thick line showing. The thick line actually shows the part of the Bode plot required. So this is only the part of the Bode plot due to what? This is actually due to 4 by j omega. Now this won't be having now after this point, this will not be having the effect of 4 by j omega only. This will be having the effect of 1 by 1 plus j 0.5 omega. What do you mean by corner frequency? It is at the corner, after the corner frequency, this term is showing a minus 20 dB per decade. Now already this graph is showing what? This graph is having a 20 dB per decade fall. Now, at 2 radians per second, as per this data, at 2 radians per second, it is encountering this term, which gives you a slope of minus 20 dB per decade, in addition to this already minus 20 dB per decade fall. So when the first order at 2 radians per second, this will be offering a minus 20, and already minus 20, adding that together you will be getting minus 40. So from this point onwards, this magnitude plot is going to have a variation of minus 40 dB per decade. Now the question is how to draw minus 40 dB per decade from this point onwards. Now keeping this point, what will be 1 decade after this? So if this is 2, then you can find out the, okay, so if this is 2, you can find out this value. This will be the 20, or this will be the point, right? This will be the point. Okay, so this will be the point corresponding to what? Corresponding to 20. So this is 1 decade, right? Comparing to this point, this one is 1 decade. Now as this frequency moves in this way, say if you can find out the 40 dB. So as the magnitude travels from this point to this point, that means it has covered a decade. Now when it has covered a decade, it has to move 40 decibel. Now corresponding to the 0 dB, what is the 40 decibel? This is the 40 decibel, right? So what must be the corresponding 40 decibel, negative 40 decibel from here? So it has to be, look, if this is 40, then what must be this point? Now you can find out from like this, right? So you may just count the number of lines, horizontal lines, 1, 2, 3. So if you can count that much value, 1, 2, 3. So this must be what? This must be 40 dB difference, right? So this is 20, this is another 20, so altogether 40, and the corresponding point will be, so this is actually your, okay, I will be marking this. This is 1 decade, right? Okay. Now look at this. You can join this point, right? Okay. Now, what does this suggest? If there would not have been a term like this, if there was only a term by k 4 by j omega, then this plot would have gone in this way. But because of the impact of 1 by 1 plus 0.5 j omega, because it introduced another minus 20 dB. So look at the change in the slope. This was already like this. Because of that, it has changed to this. So what must be the fall? This fall will be minus 40 dB per decade, right? This must be minus 40 dB per decade. So you can have the dark lines. Okay, you can darken this up to which point you can dark. Anyway, what must be your next corner frequency? Look at the corner frequency. That is 12.5 radians per second. So anyway, without any hesitation, you can move up to this point, right, over this line. You can make the point without any hesitation. Why? Because even this point is only 10 radians per second. Now what is 12.5? Now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 12.5 comes around like this, right? This is 12.5. Okay, so from this till this point, what you can do is you can add the lines. So this is 40 dB per decade. Now at 12.5, what happens? The second first order term comes into play. That means it again offers another minus 20 dB. Already this is having a 40 dB, so it will give you another minus 60 dB. Now how to plot that minus 60 dB per decade from this? Now the thing is that you need to find the next decade at, say, somewhere over here. Okay, so this must be 12.5. So this is This is the decade, and which must be the 60 dB point corresponding to this. Now the 60 dB point, so from this, this is 1, 2, 3. Okay, now if you can find out the, now what about the 60 dB? Now from this point, the 60 dB is this. Okay, so this must be minus 80, okay, minus 100 and so on. Okay, so now look at this. From minus 20 to get the 60, you need to get, so this is actually this difference. This difference is minus 60 dB, right? So if that is the case, what must be this value? What must be this value? This value must be, okay, must be what? This value must be, say, 1, 2, 1, 2, 3. So you can have this three divisions down. 1, 2, 3. This must be the point, right? Right? Okay. So what else? So this is actually your 2.5. Right? This is your 10, and this is your decade. Okay, so this is actually your 60 dB. From this point, minus 60 dB comes over here. Okay, so you may do that by yourself. So anyway, what you're going to get is, if you can straighten this point, what will be this? So you can notice that it would have, if there would not have been a third term like this Bode plot would have gone like this. But because of this, from 12.5 onwards, this is having another effect, that is 60 dB per decade. Okay, make sure that you always write the slope over the each segment of lines. That is very important. Okay, hope you understood this. Why? What is the effect? So this is actually, this minus 40 and minus 60 are all the cumulative effect. So it actually had only minus 20 dB. Now at 2 radians per second, the first corner frequency came. Because of that, it offered a minus 20 dB. So cumulatively, that becomes minus 40. And after 12.5, right? After 12.5 radians, then again comes the second corner frequency. So because of the impact, it is already having a minus 40 in, and cumulatively that become minus 60 dB per decade. Okay, now this is it. Now this plot is what is called as the magnitude plot. Now let us see some of the observations, some of the important observations from this, from the magnitude plot. So the most important is, we are concerned with this is actually the magnitude plot. We are concerned with the frequency of the magnitude plot which crosses 0 dB line. So you know which is the 0 dB line. Now you must see the frequency at this point. What is the frequency at this point? Now you can see that the frequency at this point is going to be, all right, what's going to be the frequency at that particular point? Okay, so when you just go through that, you can see that this is 2.7 radians per second. So you can see that this is 2.7 radians per second. Now why this is 2.7 radians per second? This is 2. So actually this is 1 radian. So this represents 1 radians, this represents 2, this represents 3 radians. So that means it is a point. This is a, I mean, if you carefully draw, you can you will be able to get the exact value. So this is actually a value that comes in between 2 and 3. So when you note, it will be the 7th division. So this is 2.7 radians per second. So you can see that the frequency at which the magnitude plot crosses the 0 dB is found out to be 2.7 radians per second, and this frequency is what is called as the gain. This is actually gain, right? This is called as the this magnitude plot is the gain crossover frequency. Okay, so this is gain crossover frequency, right? Fine. Okay, so hope you understood this. So your GCF is 2.7 radians per second. Now what must be the next step? Next step is to obtain what? Obtain the phase plot. Okay, now we will be doing this phase plot in the same graph. We are not going to use another graph. It is important that you always do that in the same graph, because we need to compare with this, compare the phase plot and gain plot, and based on that we can assess the stability. So it will be very easy if you can draw that in the same graph. Now the next question is, there is another challenge, where will you plot the phase? Now this axis is actually we have meant for the magnitude. If that is the case, I am using this as for the phase. Okay, now okay, so this the reference of this phase, the reference of the magnitude was 0 dB, while the reference of the phase I am taking this as minus 180 degree. So always make it a point that this minus 180 degree has the same significance, has a significance in the phase plot just as the 0 dB is having in the magnitude plot. So that's why I am I am marking this 0 dB or this minus 180 degree in line with the 0 dB axis. Okay, so both the 0 dB axis and minus 180 degree coincides. So in that way you can use this side for the phase. Okay, now you have equal divisions, right? So you can have minus, okay, so you can have minus 150, then next is minus 120, so this will be minus 210, then this will be minus 240 degree, and so on. Okay, now when you draw, I think I have just raised a bit further. It's not a problem anyway. Now when you start drawing, I suggest you to draw from this side. For this problem, mark this as the 0 dB. Okay, now anyway, we'll just try to plot the graph. Now what must be this angle? How to obtain the phase plot? Now in order to obtain the phase plot, you need to get the angle of this transfer function. Now the angle of the transfer function is given by, okay, now what is the angle of this 4? So you are actually going to find out the angle of this. Now how will you calculate the total angle, total phase? The angle of the numerator minus the angle of the denominator. So what is the angle of this? This is 0. Minus what is the angle of this? This is, yeah, tan inverse omega by 0, which is minus 90. So this will be 90. So this is 0 minus 90. So your you can see that this will be minus 90. Now the next term is tan inverse. What is the next angle? Here the angle is tan inverse 0.5 omega by 1. This will be tan inverse 0.08 omega by 1. So what you are to do is you need to subtract that, minus 90 minus tan inverse omega 0.5 omega minus tan inverse 0.08 omega. Okay, now when you draw, you are putting some arbitrary values starting from 1 to 50. Okay, now 1, 2, 8, 10, 20 and 50 and so on. So on substituting, simple substitution, you will be getting these values: minus 121, minus 144, 202 and so on. Okay, now you can plot this in this graph. Now this is how you need to plot. So actually your 1 radians per second is this, right? This is your 1 radians per second. This is the line. So at this point, you need to, anyway, even though this axis is marked on the right half, you need to start drawing from the left side. So minus 121, I will mark this. So you have already, okay, no problem in doing this. This is 120, then at 1 radians per second. Now similarly you can have so altogether you have 30, the difference is 30 between minus 120 and 50, and you have 10 divisions. So that means each division will be 3 units each. So 120 and 121 will be coming almost the same at the same point. So it's not a problem. Now what is the next value? Next value is 2. At 2 radians per second it is minus 144. Now where is this 144 comes? So this is the point at 2, and 144 is actually, this is 150, 147, so this is 144, I think, yes, right. So this is 147, this is 144, this is 144, minus 144 is this. Okay, 3. Now when you reduce 3, this is going to be a 144. And similarly you can have the graph of the other. Now when you plot 8 radians per second, it is 202. Now 8 is 8 you will be getting somewhere over here, so that will be at 202. Now where is this 202? So this is the point. Okay, this is the point at 2. Now 202, look at this, this is minus 210. So this is 27, 207, 204. Okay, so you can have this as the third line from this. 1, 2, 3. Okay. Okay. Okay, you can mark over here. Now you may just draw by scale. Just join the lines by scale, and it will be going like this. Okay, right. Now this is actually your phase plot. This is your phase plot, and this one is your magnitude plot. This one is your magnitude plot, and this one is your phase plot. Okay, now we are interested in, now next is from the observation from the phase plotters, what you need to get is, we want to obtain the frequency of the phase plot at minus 180 degree line. So minus 180 degree line is in line with 0 dB, or ineffectively you just need to find out the phase plot which crosses the 0 dB. Now you can simply note that this is 5 radians per second, right? This is 5 radians per second. Now you can identify that frequency to be 5 radians per second, and that is called as phase crossover frequency. Now what do you mean by phase crossover frequency? Phase crossover frequency is the frequency at which the phase plot crosses minus 180 degree, which crosses, mind, don't say it to be 0 dB, because 0 dB has nothing to do with the phase plot. 0 dB is connected to magnitude plot, even though we plot 0 dB and minus 180 degree in line, right? So when you come to the definition, you should write it is the frequency of the phase plot at minus, which crosses minus 180 degree line, and that is called as a phase crossover frequency, or PCF is equal to 5 radians per second. Okay, this is it. Now from this observation, we are going to do we'll be doing going to do the first. We have the in our question you have the gain margin, closed loop stability. Now I'm going to tell something about the closed loop stability. In the next session we will understand what is this gain margin, phase margin. Okay, now you can see that this is gain GCF. Based on the value of GCF and PCF, you can ascertain about the stability. Since GCF is less than PCF, the system is a stable system. Okay, so in this case, the system is a stable system because GCF is less than PCF. So what are the other conditions possible? Now there can be a situation where GCF is equal to PCF and GCF can be greater than PCF. Now in this case, when it is greater, when GCF is greater, it becomes an unstable system. This is called as a marginally stable system. Okay, marginally stable system, right? So that's it. Okay, hope you understood this. Now this is it. So when GCF is less than PCF, it is a stable system. GCF equal to PCF, it becomes a marginally stable system, and GCF is greater than PCF, it's an unstable system. Now in this, from this problem, we understood that GCF is less than. So this system, which is represented by this transfer function, is a stable system.